Solving differential equations by integration. We need to separate the variables, so we have all of the y terms on one side, all of the x terms on the other side, and then we integrate. Example 1, we're looking for the general solution to this differential equation, so we need to separate the x and y terms, like so, and I've put a 1 in here so that when we integrate 1 dy we get y. Now you do get a constant of integration on each side, but I've combined the constants into a single constant, so this is called the general solution to this differential equation. Now given x and y values, so coordinates on the curve, we can evaluate c. So if the curve goes through this point, x is 0, y is 0, so c is equal to 0, like so. If it goes through this point, x is 0, y is 1, so then c will be equal to 1. So then we have these equations, and these are referred to as particular solutions. And we can sketch each of these, and then you will see a family of curves, each with a different value for the constant of integration. So the one in red, where c equals 1, is this one. The one in black, where c equals 0, is this. And the one in blue, where c equals -1, is this curve. So we have general solutions, like so, where you have a constant of integration that has to be evaluated, and then you have particular solutions, like these, where we are given information about a point on the curve, so we can evaluate the constant, and then we get a particular solution. And together we have a family of solutions. Example 2, so we can see there's a mixture of x and y on both sides, and we need to separate the variables, like so. So I've divided both sides by the 1 plus y, then I've multiplied both sides by dx, so now the variables are separated, and when we integrate, this side here is just a constant over a linear function, so we get logs on this side, like so. We have a constant of integration, and to get rid of the log I need to do its inverse, which will be e to the power of. So if you do e to the power of on both sides, like so, e to the power of, you write e once on each side. What you're not doing is writing e underneath every single term like this. That's wrong. The e and the ln will cancel, so you get 1 plus y on the left hand side. On the right hand side, if you just look at the way we're working with indices, if we've got this power and we're adding this power, then we've got two terms with the same base there, and we're multiplying the terms, so we can add these indices like this. So all I've done is I've split this up into separate terms. Now e to the power of c is just a constant, so I'm going to replace e to the power of c with a. So then I get this, where I've moved the 1 to the right hand side, like so. So this is the general solution for this differential equation. Example 3, again we're looking for a general solution. Let's separate the variables. Okay, that's done. Integrate. Again, to get rid of the logs on each side, we do e to the power of, but you write that once on each side, like this. So all of this, including that constant, is in the power. The e and the ln cancel on the left hand side. On the right hand side, because we're adding indices, so I'm adding this power to this power, I can split this up into two separate terms with the same base, and I'm multiplying them. E to the power of c is a constant. I'm going to replace it with a. The e and the ln function inverse, they will cancel, so we will get secant x from this part. That simplifies just to secant x, and that's going to be a, so it'll be a times secant x, like so, and this is the general solution of this differential equation. Example 4, again the general solution to begin with, so we need to separate the variables, factorization on the right hand side first, separating the variables, integrating, and we need to work on the algebra on the right hand side, so we've got terms that we can integrate. These two terms will give logs, like so, and then we do e to the power of on each side. The left hand side is simple, the e and the ln cancels to give y. On the right hand side I've split up my e to the power of term into 3 separate terms. They have the same base, they're all being multiplied, which means when we look at the laws of indices that you would add these indices to get exactly this. And the e and the ln here can cancel. That is just a constant. E to the power of c is a constant. So this term gives x here. This I've replaced with a new constant a here, and that I've just copied over here. So this is a general solution to this differential equation. Now for a particular solution, you need coordinates of a point on your curve. So if we substitute these in to our general solution, so e to the power of 4 goes here and minus 1 goes into here and here, we have this, and then simplifying gives this, and now we can work out the value of a, which is minus e cubed. Now this value we need to substitute back into here and then simplify like this, and there's a base e, there's a base e there, so these indices can be added together like so, and this is a particular solution to the original differential equation. For practice, try these questions.